right now, as you listen to my voice, the audio data you are hearing isn't flowing to your device in a continuous, smooth stream.
No, not at all.
It is being violently chopped into thousands of tiny pieces, fired randomly across the bottom of the ocean or, through the air alongside millions of other people's bank transactions and cat videos.
Just an absolute torrent of data.
Yeah, and then it's frantically glued back together by your phone just milliseconds before it hits your ear.
It is absolute chaos under the hood.
Yeah.
I mean, the miracle is really that you, the listener, don't notice the violence of that process at all.
It's mind-blowing when you stop to think about it. Usually when we look at massive human infrastructure, like a suspension bridge or the electrical grid or a skyscraper, we know there's a master blueprint.
Right, someone signed off on it.
Exactly. There is a central architect. You can look at a steel beam and know exactly who placed it there and why and who is responsible if it breaks. But today, we are going to deconstruct the largest engineered artifact in human history, which is the internet. And the first thing you realize is that the blueprint is, well, it's completely missing.
Completely missing. Because it was never designed as a single cohesive entity. I mean, no single corporation owns it. No government administers the entire thing. And perhaps most terrifyingly, nobody can just flip a switch and turn it off.
Which is wild to think about.
It really is. It is the ultimate example of decentralized emergent complexity. But to truly understand how it functions, we have to look at the internet through two completely different, almost contradictory lenses.
Which brings us to the core mission of this deep dive. We want to understand not just what the internet is, but why it behaves the way it does. We are going to dig into the physical cables, the hidden math that keeps it cheap, and the invisible wars happening right now to control your data.
So much of it is completely invisible to the user.
Right. So you mentioned these two competing lenses. Let's start there. What am I actually looking at when I look at the internet?
So the first lens is what engineers call the infrastructure view. If you zoom out and look at the physical reality of the Earth, the internet is a radically fragmented, hyper-commercial, constantly shifting federation.
Federation is a good word for it.
Yeah, we are talking about tens of thousands of independently operated networks. It is a messy amalgamation of fragile glass fiber optic cables running across tectonic plates on the ocean floor, ancient copper wires snaking into our basements, radio spectrum carrying Wi-Fi and 5G, and massive industrial routers pushing hundreds of terabits of data per second.
Just a total mishmash of hardware.
Exactly. It is wildly heterogeneous. Every network is built differently.
So it's basically thousands of rival companies and sovereign nations using completely different physical technologies, duct taping their networks together at the borders and just hoping for the best.
That is a surprisingly accurate description, yeah. But then you switch to the second lens, which is the service view.
Okay, what does that look like?
From the perspective of the application sitting on your phone, whether you are streaming a 4K movie, sending a secure email, or playing a real-time video game, the internet lies to you.
It lies.
It does. It presents itself as incredibly simple. It offers a single, uniform, minimal, and completely frozen contract to your apps. And that contract is officially known as Best Effort Datagram Delivery.
Best effort datagram delivery. That sounds a bit like, I don't know, walking into a post office, handing them a letter, and the clerk says, hey, we'll try our best, but no promises.
That is practically the literal translation.
Yeah.
An application hands the network a packet of data with a destination IP address. The network says, I will try to deliver this, but it gives you zero guarantees.
Zero.
None. There's no guarantee your data will arrive. No guarantee it will arrive on time. No guarantee the packets will arrive in the order you sent them. And the network won't even notify you if it drops your data into a black hole.
Wait, hold on. So every single service we use online, perfectly synced FaceTime calls, secure banking encryption, reliable massive file downloads, all of that has to be built by the computers at the very edges to compensate for a network that fundamentally promises nothing.
Yes, the network interior is completely dumb and unhelpful. The computers at the edge do all the heavy lifting to make it look reliable.
Why on earth would anyone design the most important communication tool in human history that way? We have this chaotic physical mess offering a highly unreliable service contract.
To understand the why, you really have to look at the bizarre historical constraints placed on the original engineers. The internet isn't a clean mathematical solution to a single problem.
Right, it didn't just spring out of nowhere.
No, it's the messy residue of historical decisions made in the 1960s, 70s, and 80s. The original design brief for what evolved out of the ARPANET was essentially this: figure out how to interconnect networks that fundamentally do not trust each other, are built using entirely different physical technologies, and are run by organizations with conflicting commercial or military interests.
That sounds like a nightmare.
Oh, and you can't have a central operator.
That sounds less like an engineering assignment and more like a cruel joke, like build a global telecommunications network, but nobody trusts each other and you don't own any of the parts. Good luck.
But they did it. And as we'll see, the things about the internet that seem incredibly inefficient or strange to us today are actually highly rational, brilliant answers to that exact historical brief.
Well, let's start with the most primal problem of communication, because before you can stream Netflix, you have to physically send an electromagnetic signal from point A to point B.
Right, you need a physical medium.
And a physical links, like burying thousands of miles of fiber optic cable across a continent or launching satellites, those are staggeringly expensive. But human demand for those links is incredibly erratic. The term I always hear engineers use is bursty.
Bursty is the fundamental characteristic of human data. Think about your own behavior when you browse the web. You click a link to load an article. For a fraction of a second, your computer demands a massive, sudden spike of data from the network.
Like, it needs it all right now.
Exactly. And then, for the next 3 minutes, you just sit there silently reading the text. You demand absolutely nothing. Human communication is inherently unpredictable and clustered in sudden bursts.
So the debate at the dawn of network engineering was, how do we share these incredibly expensive physical cables efficiently, knowing that humans are going to use them in these chaotic bursts?
Exactly. And there were two fundamentally opposed philosophies on how to solve this. The first option, the old school way, is circuit switching.
I try to visualize circuit switching like making a VIP reservation at a very exclusive restaurant. You call ahead, you reserve a specific table for the whole night, the maître ropes it off. Even if you get up to go to the restroom for 20 minutes or go outside to take a phone call, that table is yours. Nobody else can sit there, even if there's a line of people waiting outside in the rain.
That is the perfect analogy. The traditional century-old telephone network is the canonical example of circuit switching. In that system, before you can even say the word hello, the network sends signaling messages ahead of you across the country to establish a dedicated physical end-to-end path.
So it's mapping the route before you even speak.
Right. It reserves a fixed chunk of capacity on every single wire, switch, and microwave tower along that path for the entire duration of your call.
And it does this by literally carving up the physical capacity of the wire, right? How does a single copper wire carry multiple VIT tables at once?
It partitions the capacity using multiplexing. The two classic methods are frequency division multiplexing, or FDM, and time division multiplexing, PDM.
Let's break those down. What's FDM?
In FDM, the link's electromagnetic spectrum is sliced into different frequency bands. Think of it like different stations on your car's FM radio dial. Your phone call gets assigned one specific frequency band, and it gets to use that band continuously.
Okay, that makes sense. And TDM?
In time division, time itself is sliced into fixed repeating frames. Let's say a frame is divided into 24 time slots. Your call might get assigned slot number 7. So slot 7 over and over and over again belongs exclusively to you.
I can see the appeal of this. If I have that VIP table, the trade-off is incredibly clear. I get a guaranteed rate of data, and I get a constant, unwavering delay. Once my call is connected, there is no waiting in line.
Yes, in network terms, there is zero queuing delay.
I speak, the signal travels at the speed of light, and you hear it.
Yes, and there's absolutely zero packet loss due to network congestion. If the network is full, your call just doesn't connect. But if it connects, the quality is flawless. Those are the exact properties that early 20th century voice telephony required.
But the price we pay for that VIP table is astronomical waste, isn't it?
It is economically devastating for computer data. Let's look at a phone call. Human conversation is silent about 60% of the time in each direction. You ask a question, you pause, you listen to me, you breathe.
Right, there's naturally a lot of dead air.
In a circuit switch network, during those silences, that reserved frequency band or that dedicated time slot is just sitting there, empty, utterly wasted. The network cannot let anyone else use it.
And the other penalty is what happens at the front door of the restaurant. If all the VIP tables are full, the bouncer turns you away entirely. If all the circuits in a phone network are busy, you pick up the receiver, you don't get a dial tone, or you hear a fast, busy signal.
We call that the blocking probability. And funnily enough, that blocking probability is governed by a classical mathematical formula published in 1917 by a Danish mathematician named A.K. Erlang.
1917, wow, that's old math.
Yeah, the Erlang-B formula is still used today to calculate how many cell towers you need in a city to ensure people don't get blocked on Mother's Day when everyone calls home at the same time.
That makes total sense.
But reserving enough capacity for the absolute worst-case peak demand is economically absurd for modern internet traffic. The ratio between your peak burst demand when you load a 4K video and your average demand over the whole day can easily be 100 to 1 or even 1,000 to 1.
Which perfectly explains why the architects of the internet chose the completely opposite path, which is packet switching. If circuit switching is the VIP restaurant reservation, packet switching is a chaotic, crowded food truck festival.
I love that. A food truck festival.
You just show up, you don't call ahead, you chop your data up into little pieces, which are the packets, you slap a destination address on the front of each one, and you just hurl them into the crowd as fast as your connection allows, hoping they make it to the other side.
It's a completely different paradigm. There are no reservations. There's no signaling ahead to set up a path. And because of this, the routers inside the network have to operate on what we call a store and forward discipline.
Store and forward. Walk me through exactly what a router does when a packet hits it.
When a router receives a packet on a wire, it has to pull the entire packet into its memory first. It stores it. Then it looks at the destination IP address in the packet's header. It consults its map, picks the best output link to get the packet closer to its destination, and pushes it forward.
But what if that output link is already busy? What if someone else's packet is currently being pushed out onto that exact same wire?
Then your packet has to wait. The router places your packet into a buffer, which is just a fancy word for a waiting line or a queue. And if the network gets extremely busy and that buffer fills up completely, well, the router simply drops your packet.
It just deletes it.
It deletes it from memory. It falls on the floor and ceases to exist.
So the trade-offs completely flip. With packet switching, we completely lose the guaranteed speed. We lose the constant predictable delay because our packets might have to wait in line for unknown amounts of time. And we suffer packet loss if the network gets overwhelmed. That sounds terrible. Why would we choose this?
Because of the efficiency. Reaching absolute maximum efficiency of these expensive physical wires. An idle user, someone reading a web page, consumes absolutely zero network capacity.
And this introduces a concept that I think is the secret economic engine of the modern world. Let's talk about statistical multiplexing, because this is the math that makes the internet affordable for everyone listening.
Statistical multiplexing is the sharing of a resource based on the statistical probability of demand, rather than reserving for the worst-case scenario. Let's break down the math with a concrete example.
Okay, let's say we have an expensive fiber optic link that can transmit exactly 1 megabit of data per second. And we have a group of users who, when they are actively doing something, each need 100 kilobits per second. But because they are humans, they are only actively downloading data 10% of the time. The other 90% of the time, they are reading, thinking, or staring at the screen.
Under the old circuit switch model, the telephone model, you are forced to reserve that 100 kilobits per second for every single user permanently, just in case they decide to be active. So on a 1 megabit link, which is 1,000 kilobits, you can fit exactly 10 users.
1,000 divided by 100.
Right. That is the absolute hard limit. When user number 11 tries to log on, they get a busy signal.
But with packet switching, we don't reserve anything.
Right. We let everyone share the 1 megabit pool dynamically. We just need to ensure that the instantaneous aggregate demand of all the users rarely exceeds 1 megabit at the exact same millisecond.
So how many users can we cram onto that same wire?
Well, since each user is independent and only active 10% of the time, we can use binomial probability. If we put 35 users on that exact same 1 megabit link, what are the odds that more than 10 of them will suddenly decide to click a link at the exact same millisecond?
Just intuitively, if they're only active 10% of the time, getting 11 out of 35 to spike at the exact same fraction of a second feels like it should be pretty rare.
It is vanishingly rare. The probability is roughly 4 times 10 to the negative fourth. That means with a probability greater than 99.96%, the instantaneous demand of those 35 users will perfectly fit into the exact same capacity that circuit switching would have exhausted at just 10 users.
That is incredible. We get a 3.5x gain in the number of paying customers we can put on the exact same physical wire just by changing the math of how they share it.
And that is why your internet bill is $50 a month instead of $5,000 a month. The entire economy of the internet relies on this gamble.
Let me play devil's advocate here. It is a gamble, right? A mathematically sound gamble, sure. But what happens during that 0.04% of the time when 12 people do click at the exact same millisecond?
That's where the buffers come in. When the instantaneous demand exceeds the 1 megabit wire speed, the router just holds the extra packets in memory for a few milliseconds until the burst subsides. The users might experience a tiny, imperceptible lag spike, but nobody gets blocked or disconnected.
And as you scale this up from 35 users to 35 million users, does the gamble get riskier?
Actually, the math gets infinitely better. There's a powerful statistical concept called the square root of n smoothing principle.
Explain that for me because it sounds like a physics law.
It essentially is a law of large numbers. It means that as you aggregate more and more independent bursty users together, as the number n gets larger, their peaks and valleys cancel each other out.
Oh, I see.
The required capacity per user drops dramatically and approaches their average demand, not their peak demand. The safety margin, or the buffer you need to build into the system to handle the spikes, only grows at the rate of the square root of n, while the total traffic grows linearly at the rate of n.
That perfectly explains the physical reality of the internet today. The incredibly massive links deep in the core of the internet, like the submarine cables crossing the Atlantic carrying millions of different users simultaneously, they run incredibly smoothly. They don't look bursty at all. They look like a steady, continuous hum of data at high utilization.
Precisely. The core is smoothed out by the law of large numbers. But the access links at the extreme edges, like your home Wi-Fi router, which only has 3 or 4 people on it, don't benefit from that massive statistical smoothing. So the edge remains incredibly bursty, erratic, and mostly idle.
Before we move on from the genius of packets, a very basic structural question. Why do we chop files into tiny packets in the first place? If I want to send a 5 megabyte photo of my dog to my mom, why not just send one giant 5 megabyte packet?
That comes down to a brilliant mechanical trick called pipelining. Remember that routers use a store and forward discipline. A router has to receive the entire message into memory, verify it, and then begin sending it out the other side.
Right.
Imagine if you send that massive 5 megabyte photo as one single unsegmented chunk across a path of, say, 10 routers. The first router has to swallow the entire 5 megabytes. That takes time. Only when it has the whole thing does it begin pushing it to the second router. The second router waits to swallow the whole thing. It is a completely sequential start and stop process.
I see. It's like moving a giant 1,000-pound boulder down a line of people. I have to wait for you to fully hand it to me. I have to balance it, and only then can I turn and slowly hand it to the next person.
Yes, but if you take that 5 megabyte photo and segment it into thousands of tiny packets, you fundamentally alter the physics of the transfer. It turns a sequential delay into a high-speed parallel pipeline.
Like a bucket brigade. Instead of one boulder, we are passing hundreds of small buckets of water.
Exactly. While the first router is receiving the second packet from you, it is simultaneously forwarding the first packet to the second router, and the second router is simultaneously forwarding it to the third. You overlap the transmission times.
That saves so much time.
It does. For a long path with many hops, the end-to-end delay shrinks dramatically. It mathematically approaches the time it takes to transmit the data over just a single link, rather than multiplying the delay by every single router on the path.
That is such an elegant solution. But if smaller is faster, why not make the packets microscopic? Why not send one byte at a time?
Because of the metadata tax. Every single packet, no matter how small the payload, requires a header. The header contains the destination address, the source address, sequence numbers, and routing flags.
So you're attaching a full address to every single byte.
Yes, and if your packet only carries 10 bytes of actual photo data, but it requires 50 bytes of header information just to navigate the network, you are wasting 80% of your expensive physical bandwidth on digital envelope paper.
So there has to be a Goldilocks zone. Not too big that it ruins pipelining, not too small that you drown in overhead.
Exactly. The engineering optimum ended up being a moderate size. For Ethernet, which is the link technology that dominates the modern internet, the maximum transmission unit, or MTU, is usually 1,500 bytes. That's a compromise struck by engineers in 1980, and because it was baked into the hardware worldwide, it has essentially become an unchangeable, universal constant of the internet.
Okay, so we've got millions of people throwing 1,500 byte packets into a statistical soup. Let's look at the actual anatomy of how these networks connect to form the physical internet. We can broadly divide the landscape into two zones, the edge and the core. The edge is where you and I live, It's our laptops, our smart TVs, our phones connecting to our first hop router via Wi-Fi, 5G, or a cable modem.
The edge is fascinating because it is deeply shaped by early assumptions about human behavior.
Well, one thing I've always noticed when shopping for home internet, whether it's cable or DSL, is that the speeds are almost always wildly asymmetric. My ISP will advertise a download speed of, say, 500 megabits per second, but if I look closely at the fine print, my upload speed is capped at maybe 20 megabits per second. Why do they throttle my upload so aggressively?
It wasn't originally designed to throttle you out of spite. It was a highly deliberate physical engineering choice made decades ago. When broadband technologies like DOCSIS, which is the protocol used for cable internet, and DSL, which runs over old telephone wires, were invented, the engineers made a foundational assumption. They assumed residential users are primarily consumers of content, not creators.
I guess in the 1990s that made sense. I sent a tiny few byte mouse click requesting a web page and a massive wall of images and text streams down to me.
Right. The physical spectrum on a coaxial cable or a copper wire is limited. You only have so many radio frequencies you can use. So the engineers permanently allocated far more of the physical spectrum to the downstream path from the network to you than the upstream path. They physically hardwired the asymmetry into the modems and the neighborhood nodes.
But that assumption is completely breaking down today, isn't it? If you're working from home, running a high-definition Zoom call, you are transmitting just as much video data up to the cloud as you are pulling down. If you're backing up your hard drive, or if you're a teenager live streaming a video game, you are suddenly a massive creator of data.
It is severely straining the edge infrastructure. When millions of people suddenly started working from home, they found that their 20 megabit upload links were completely saturated by multiple family members doing video calls simultaneously. And it highlights a universal truth in network measurement that most consumers don't realize. The edge is almost always the true bottleneck.
What do you mean by that?
People tend to blame the internet when things are slow. But the core of the internet, the massive fiber optic backbones connecting cities, is generally vastly over-provisioned. The primary source of delay, the place where packets actually get dropped, and the absolute limit on your speed is almost always your local access link. In fact, most of the time, the bottleneck isn't even your ISP's cable in the street, it's the Wi-Fi router sitting in your living room, fighting over congested radio spectrum with your neighbor's Wi-Fi router.
That's a great practical tip for anyone listening. If your connection is terrible, try plugging a physical Ethernet cable into your laptop before you spend 3 hours on hold with your ISP. So that's the edge. But what happens when our packets leave our neighborhood and enter the core? This massive mesh of high-capacity routers and global links. How does a router in Chicago actually know which wire leads to a server in Tokyo?
To understand the core, you have to separate it into two logically distinct functions. This is arguably the most important conceptual division in all of computer networking. We have the data plane, and we have the control plane.
Okay, the data plane and the control plane. Those sound like terms from a sci-fi cockpit. Walk me through them.
Think of the data plane as the local, unthinking, reptilian reflex of a single router. A packet arrives on an input wire. The router's hardware looks at the destination IP address, checks its internal forwarding table, finds a match, and aggressively shoves the packet out a specific output port.
So it's like a mail sorter in a post office who just looks at a zip code, matches it to a bin on the wall, and tosses the envelope in. They don't think about the geography of the country, they just execute the local rule.
Exactly. And because the data plane is so simple, it is entirely hardwired into specialized silicon chips called ASICs. This allows it to happen on nanosecond timescales. A massive core router is performing this mindless reflex billions of times per second. It is local and is incredibly fast.
But wait, how does the router know which zip code goes to which bin in the first place? Who programmed the forwarding table?
That is the job of the control plane. The control plane is the brain. It is the global network-wide process where all the routers constantly talk to each other to compute the map of the internet.
How do they talk to each other?
They run complex routing protocols. They exchange millions of messages saying, hey, I just lost connection to this cable, or I found a faster path to Tokyo. This happens in software over timescales of seconds to minutes. The control plane's entire job is to constantly observe the changing topology of the world, solve massive graph theory math problems to find the shortest paths, and then push those answers down into the mindless forwarding tables that the data plane uses.
I love that distinction. The data plane is the fast reflex. The control plane is the slow, calculating brain drawing the map. Now, speaking of that map, we established earlier that nobody owns the whole internet. It's stitched together by tens of thousands of different networks, which engineers call autonomous systems, or ACEs.
Yes. Verizon is an autonomous system. Google is an AS. The University of Michigan is an AS. Your local regional ISP is an AS.
I try to imagine it like a fragmented globe of sovereign nations. If Verizon and Google don't have a boss and there's no supreme global president of the internet telling them what to do, how do they actually decide who carries whose traffic? I assume a lot of money changes hands, right?
Absolutely.
Yeah.
Because there's no central authority, the global topology of the internet self-assembles purely out of bilateral commercial contracts. It's capitalism drawing a map. And there are two canonical forms of these business deals, transit and peering.
Okay, let's unpack those, starting with transit. If I'm a small ISP in Ohio and my customers want to watch YouTube, check a bank in London, and read a blog hosted in Australia, how do I get them there?
You buy transit. Transit is a customer-provider relationship. The small Ohio ISP pays a larger global network, often called a Tier 1 provider like AT&T or Lumen, for a transit connection. The larger network signs a contract that essentially says, if you pay me a fee based on the volume of data, I promise to carry your traffic to literally everywhere on planet Earth and deliver the world's traffic back to you.
Got it. Transit is a product. I am paying for universal global connectivity. What about peering?
Peering is a completely different dynamic. It's a settlement-free exchange. This happens when two networks, let's say a large regional ISP and a massive content provider, look at each other and realize they have a mutual problem.
What's the problem?
They are both paying massive fees to their transit providers. The ISP says, my customers are requesting terabytes of video from you. The content provider says, I'm sending terabytes of video to your customers. Instead of both of them paying their expensive global transit providers to route this traffic all the way up the chain and back down, they make a deal.
They cut out the middleman.
Precisely. They say, let's just run a physical fiber optic cable between our two routers right here in this city, and we will swap our mutual traffic for free. No money changes hands. It's a pure barter system to save on transit costs.
That is fascinating. But where do they physically plug these cables in? Do they just meet in an alleyway with a spool of fiber?
Close. They meet in specialized, heavily guarded buildings called Internet Exchange Points, or IXPs.
Tell me about these places, because they sound almost mythological.
They are the physical beating heart of the internet. An IXP is essentially a giant colocation data center with a massive, incredibly powerful network switch in the middle of the room. There are famous ones all over the world. DECIX in Frankfurt, AMSIX in Amsterdam, LINX in London.
So what happens inside the building?
Hundreds of different competing networks, ISPs, cloud providers, streaming services, will rent a server rack in this building. They bring their fiber into the building and plug into that shared central switch. And suddenly, because they're all plugged into the same room, they can establish free peering agreements with hundreds of other networks pairwise over a single physical port. The marginal cost of connecting to a new partner drops to almost zero.
The scale of that must be unfathomable.
It is. We are talking about double-digit terabits of data per second flowing through a single building in Frankfurt. It is a hive of commercial cooperation born entirely out of a desire to save money.
Now, when I first took a computer science class back in the day, I was taught a very neat, structured hierarchy of how traffic flowed. The model was a pyramid. I was a user at the bottom. I connected to my local ISP. My local ISP connected to a regional ISP. The regional ISP connected to a massive Tier 1 global transit backbone at the top. The traffic went way up into the sky, traveled across the globe on the backbone, and trickled back down the pyramid to the destination server.
Yes, that was the textbook transit hierarchy of the 1990s and early 2000s. And the plot twist that most people miss is that pyramid model is completely dead.
Dead. What killed the pyramid?
A phenomenon we call the flattening of the internet, driven by content distribution networks, CDNs, and the massive hypergiants.
Who are the hypergiants?
Think of the 4 or 5 companies that generate the vast majority of all internet traffic today. Google, Netflix, Meta, Amazon, Microsoft. Over the last 15 years, these companies realized that sending their massive, unimaginable volumes of video and data through that traditional multi-hop transit pyramid was too slow, too unreliable, and incredibly expensive. So they decided to bypass the internet entirely.
Wait, how do you bypass the internet?
By building your own.
Yeah.
The hypergiants started laying their own physical infrastructure. They laid their own private submarine fiber optic cables across the Pacific and Atlantic Oceans. They built massive global private backbones. And instead of buying transit at the top of the pyramid, they took their networks directly to those IXPs we just talked about. And they peered directly with the local access ISPs at the bottom of the pyramid.
Hold on. So if I'm sitting at home in Chicago and I hit play on a Netflix show, my data isn't traveling out to some global internet backbone.
Almost certainly not. Netflix has placed hundreds of CDN cache servers literally inside the data centers of local ISPs all over the world. When you hit play, the movie you want is probably sitting on a hard drive 3 miles from your house inside a Comcast or AT&T facility. The traffic never touches a Tier 1 global transit network. It travels over a short, fat direct link straight to your neighborhood.
That completely changes the mental map. The internet isn't a tall pyramid anymore. It's a flat pancake. The modern internet graph is just dominated by these massive, direct, localized connections between the eyeball networks where we live and the hypergiants who hold the content.
Exactly. If you try to analyze modern internet performance or network neutrality debates or telecom economics using that old 1990s pyramid model, you will get the answers completely wrong. The hypergiants essentially swallowed the core of the internet.
Which is the perfect bridge to our next big section. Let's talk about performance. Because at the end of the day, every listener only cares about one ultimate question. Why is my connection lagging? When my Zoom call stutters or my game freezes, what is physically slowing my packet down? You mentioned earlier that there are 4 distinct horsemen of delay inside a router. Let's break them down.
All right. Let's trace a packet as it hits a router and isolate the 4 physical components of nodal delay. The first is processing delay.
This is the data plane reflex we talked about earlier.
Exactly. This is the time it takes the router's silicon to examine the packet header, check for bit-level errors, and look up the destination in the forwarding table. Today, with modern ASIC chips, this is measured in microseconds or less. It is virtually instantaneous. It rarely contributes to the lag you feel, although it does put a hard ceiling on how many millions of packets per second a router can physically process.
Okay, processing is negligible. What's horseman number 2?
Number 2 is queuing delay. This is the time your packet spends trapped in the router's memory buffer, waiting in line for the earlier packets to be transmitted out onto the wire.
This is the food truck line.
Yes. And this is the most critical delay to understand, because it is the only component that is wildly unpredictable. It's a random variable. If the network is completely quiet, your queuing delay is exactly 0. But if there is a sudden burst of traffic, say everyone in your house starts streaming at once, your packets might wait in that buffer for tens or hundreds of milliseconds. In pathological cases of bad network design, packets can get stuck in queues for multiple seconds.
A multiple second delay in a video game is a lifetime. You're dead before you even see the enemy. Okay, what are 3 and 4? Because these two always confuse people.
Number 3 is transmission delay. This is entirely a function of the link's bandwidth, the speed of the port. It is the time it physically takes the router's network card to push all the ones and zeros of your packet onto the physical medium, whether that's flashing a laser into a fiber optic tube or oscillating a radio antenna.
So it's about the volume of data divided by the speed of the pump.
Exactly. If you have a massive 1500 byte packet and you are trying to push it out over a very slow legacy 1 megabit per second link, it takes the router 12 full milliseconds just to squirt the bits onto the wire.
And the 4th delay.
Propagation delay. This has nothing to do with bandwidth or packet size. This is entirely dictated by the unforgiving laws of physics and the speed of light. It is the time it takes the electromagnetic signal to physically travel the length of the cable from router A to router B.
So once the bits are actually on the wire, how fast do they travel?
Through the glass of a fiber optic cable, light travels at about 2/3 of its speed in a pure vacuum. So practically, it takes a signal about 30 milliseconds to cross the Atlantic Ocean one way and about 20 milliseconds to cross the continental United States. You cannot buy your way out of propagation delay. No matter how much money you pay your ISP for a faster connection, you cannot bend the speed of light. The only way to reduce propagation delay is to move the server physically closer to the user, which is exactly why those CDNs we just talked about exist.
Okay, I want to make sure I really understand the fundamental difference between transmission delay and propagation delay because they sound so similar. Let me try an analogy on you. Imagine a toll booth on a long stretch of highway. The toll booth represents the router's transmitter, and the highway represents the physical fiber optic cable. The bits of data in my packet are a convoy of 100 cars driving together.
This is a classic engineering analogy. Let's see where you take it.
Okay, so transmission delay is the time it takes for my entire 100-car convoy to slowly pull up to the toll booth, pay the toll one by one, and get through the physical gate. If the toll worker is slow, which represents a low bandwidth, slow internet connection, it might take an hour just to process all the cars and get the convoy fully onto the road. But propagation delay is the time it takes those cars, once they are actually through the gate and driving on the asphalt, to travel the 500 miles to the next city.
Perfectly stated. They are totally independent physical properties. The toll booth processing time is a function of the rate, the bandwidth. The highway travel time is a function of distance.
So if I get frustrated with a slow website hosted in Japan and I call my ISP and upgrade my home internet from a 100 megabit package to a 1 gigabit package, I am essentially just building 10 more toll booths at my house. I'm speeding up the transmission, but I am doing absolutely nothing to speed up the highway. The server in Japan is still exactly as far away, and the light takes exactly as long to travel.
Exactly. Upgrading your bandwidth does not cure propagation delay. It just pumps the data onto the long road faster.
Now let's go back to that unpredictable second delay, queuing. You mentioned that queues are random, but there is a mathematical reality governing how bad they can get. I've heard network engineers talk about a metric called traffic intensity, or rho.
Yes. Rho is the Greek letter we use to represent traffic intensity. It is the core metric of queuing theory. Rho is simply the average arrival rate of bits divided by the service rate of the link. It's a ratio of the offered load relative to the capacity.
Okay, so if I have a 1 gigabit link and I am consistently trying to push 1.2 gigabits of data through it, rho is 1.2.
Right. If rho is greater than 1, your arrival rate exceeds your service rate. You are shoving more data in than the pipe can possibly drain. The queue will grow infinitely until the router's memory fills up, and then it starts dropping every new packet. It is catastrophic failure. You never, ever want a sustained rho greater than 1.
But what if it's less than 1? What if the IT dashboard shows the link is operating at 90% capacity? Rho is 0.9. That sounds totally fine, right? We still have 10% headroom.
This is where human intuition utterly fails us, and where network administrators get themselves into terrible trouble. Because internet traffic is inherently bursty as rho approaches 1, the queuing delay does not increase in a smooth, steady, linear line. It explodes exponentially.
Explodes how?
On a graph, the curve looks like a hockey stick. If your link is at 50% utilization, the average wait time in the queue is very small. If you go up to 60%, it barely moves. But once you cross 80%, the curve goes vertical. A link that is 90% utilized isn't just slightly slower than a 50% link. The queuing delay might be 10 times larger. At 95% utilization, the delay goes through the roof.
Wow. So an IT manager looking at a green light on a dashboard seeing 90% capacity thinks we are being highly efficient with our resources. But meanwhile, the users in the office are experiencing massive, crippling lag spikes every time a microburst of traffic hits that 10% headroom.
Precisely. The link isn't full does not imply the link isn't the problem. Operating a bursty network near 100% capacity is a recipe for terrible user experience.
Which brings up a fundamental law of how things wait in line. You shared this with me in the notes, and I want to explore it because it applies to everything, not just the internet. Little's law.
Ah, Little's law. This is one of the most elegant and universal theorems in all of performance analysis, proved by John Little in 1961. It simply states that for any stable system, the average number of items in the system, let's call that L, is equal to the average arrival rate of items, let's call that lambda, multiplied by the average time an item spends in the system, let's call that W.
Okay, L equals lambda times W. Give me a real-world example so I can visualize this before we apply it to packets.
Let's use a Starbucks. Imagine you walk into a busy Starbucks and you want to know, on average, how many customers are inside the store at any given time. That's L, the number of items in the system.
Okay, I'm looking around the store.
You observe the door for a few hours, and you see that, on average, 2 customers walk in every minute. That is your arrival rate, lambda. Then you track a few customers and realize that, on average, a customer spends 10 minutes inside the store, waiting in line, getting their coffee, and leaving. That is W, the wait time.
So 2 customers per minute multiplied by 10 minutes equals 20.
Exactly. Little's law guarantees that, on average, there are 20 customers inside that Starbucks.
Why is a simple multiplication formula so powerful for network engineers?
Because it is a fundamental dimensional analysis workhorse that requires zero assumptions about the internal complexity of the system. It doesn't matter if the Starbucks has 1 barista or 5 baristas. It doesn't matter if the customers are ordering simple drip coffee or complex frappuccinos. It doesn't matter if the queue is first come, first serve, or if VIPs get to cut the line. As long as the system is stable, the relationship holds.
So if I apply this to a router on the internet, how does that work?
Well, if you know any two of those variables, the average number of packets sitting in the router's memory, the average arrival rate of the packets, or the average delay a packet experiences, you can instantly deduce the third. It is a universal truth of networks that allows us to mathematically guarantee performance boundaries without knowing the chaotic specifics of the traffic.
That is deeply satisfying. Okay, I have one more fundamental performance metric before we look at how apps use the network, the bandwidth delay product, or BDP. I've heard engineers describe this as the volume of the pipe.
Yes, the BDP is a crucial concept. It is calculated by multiplying the bottleneck bandwidth of a pass by the round-trip time, or RTT. It tells you exactly how many bits of data can be in flight at any given moment.
What do you mean by in-flight?
Think about it from your computer's perspective. You send a packet, it travels across the ocean, hits the server, and the server sends an acknowledgement packet back saying, "I got it." The time that takes is the round-trip time. Data in flight is the data that has physically left your computer's network card, but you haven't yet received the acknowledgement for it. It is literally in transit, traveling as light through the glass.
Let's do the calculation for this, because when you run the numbers on modern networks, the scale is wild. Let's say we have a massive transcontinental fiber link. Incredible bandwidth, 10 gigabits per second. But because it has to cross an ocean and a continent, the round-trip time is 80 milliseconds.
Okay, let's do the math. 10 gigabits per second multiplied by 0.08 seconds, that gives you 800 megabits. If we divide by 8 to get bytes, that is exactly 100 megabytes.
100 megabytes. That means to actually utilize the full speed of that 10 gigabit link, my computer needs to blast out 100 megabytes of data before it even receives a single message received acknowledgement from the other side.
Exactly. You have to keep the pipe constantly full. And here's the catch. Your computer needs to keep a copy of all 100 megabytes in its own local memory, in what we call a send buffer, just in case a packet gets dropped halfway across the ocean and needs to be retransmitted.
Wait, if I have to hold 100 megabytes in my computer's RAM just for one connection, what happens if I am using an older operating system or a poorly tuned protocol? What if my computer's TCP window, its buffer limit, is artificially capped at, say, 64 kilobytes, which I know used to be standard in the 90s and 2000s?
This is the tragedy of high-speed networks. If your computer refuses to have more than 64 kilobytes unacknowledged at one time, you send 64 kilobytes, and then your computer stops. It sits there paralyzed, waiting 80 milliseconds for the acknowledgement to come back from across the ocean.
But the pipe holds 100 megabytes.
Exactly. If you only send 64 kilobytes per round trip, you are using less than 1/10 of 1% of the available network capacity. You could pay for a massive 10 gigabit connection, and your actual download speed would be a miserable few megabits per second. High BDP paths, what network engineers call long fat networks, ruthlessly expose small buffers and poorly tuned software.
That is a revelation. It's not enough to just buy a bigger pipe. Your application has to be aggressive enough and have enough memory to fill the pipe, which is a brilliant transition into Section 4. If high BDP paths are ruthlessly exposing our computer's buffers, it makes me wonder how our laptops actually package this data in the first place to survive that journey. Let's look at the architecture of the internet, the 5-layer stack.
The layering model is how we organize the immense complexity of network communication. It allows software developers to write web browsers without needing to know anything about the physics of fiber optics.
Walk me through the 5 layers.
You start at the top closest to the user. Layer 5 is the application layer. This is where protocols like HTTP for web browsing or SMTP for email live. This is the language your apps speak. Below that is Layer 4, the transport layer. This is dominated by TCP and UDP. Its job is process-to-process delivery, getting the data from the specific browser tab on your laptop to the specific web server process on the destination machine.
So that's the one managing the connection.
Right. Then below that is Layer 3, the network layer. This is the famous Internet Protocol, IP. Its job is host-to-host delivery across the globe. It just gets the packet to the right destination machine, regardless of the physical path. Below that is Layer 2, the link layer, like Ethernet or Wi-Fi, which moves the packet across a single physical hop to the next router. And finally, Layer 1, the physical layer, the actual laser photons in the fiber or the copper voltages or the radio waves.
I always visualize this process as Russian nesting dolls. It's called encapsulation. Let's trace it. I write an email. The application layer creates the message data. It hands it down to the transport layer. The transport layer puts that data inside its own digital envelope and slaps a TCP header on the front.
Right, it wraps it up.
Then it hands it down to the network layer. The network layer doesn't care what's inside, it just treats the whole thing as payload, puts it inside another envelope, and slaps an IP header on it. Then the link layer slaps an Ethernet header on it. It's envelopes inside of envelopes.
And that modularity is genius. Because the layers don't care about the internals of the other layers, it allows engineers to swap out technologies without breaking the whole system. You can switch your laptop from Wi-Fi to an Ethernet cable, changing layer 2 completely, and your layer 5 web browser doesn't even notice. The connection stays alive.
But all those envelopes add weight, don't they? There is an overhead tax.
There is a significant tax. Let's calculate it. A standard IPv4 header is 20 bytes of metadata. A standard TCP header is another 20 bytes. An Ethernet header is 14 bytes. That is 54 bytes of pure routing metadata slapped onto the front of every single packet.
Okay, 54 bytes. If I'm downloading a massive file and the network is using that maximum packet size we talked about earlier, a 1500 byte MTU, then 54 bytes out of 1500 is about, what, 3 or 4%?
Exactly. For large data transfers, a 4% tax is totally acceptable for the brilliant modularity it provides. But think about real-time interactive applications. Think about a highly competitive multiplayer video game or a voice-over IP phone call.
Oh, in a voice call, I don't want to wait to fill up a 1500 byte packet with audio before sending it because that would introduce a massive delay. I want to send tiny fragments of audio instantly, right as I speak them.
Exactly. A voice codec might generate a tiny payload of just 64 bytes of audio data every 20 milliseconds to keep latency low.
But wait, if my actual payload is 64 bytes and I have to attach the mandatory 54 bytes of IP, TCP, and Ethernet headers to it,
Your overhead ratio is massive. Nearly half the data you are transmitting over the physical wire and paying your ISP for is just digital envelope paper. It's almost a 45% tax.
that is brutally inefficient.
It is. And over the decades, whenever network engineers look at that inefficiency, they get tempted to optimize it. They say, let's compress the headers, let's merge the network and transport layers for voice calls to save space. But they usually don't, because doing so destroys the modularity that made the internet evolvable in the first place.
Which brings us to the most important architectural feature of that entire 5-layer stack. If you draw the protocols out on a whiteboard, it doesn't look like a straight cylinder. It looks like an hourglass.
Yes, the famous hourglass model of the internet. At the top of the hourglass, the application layer, it is wide open. There are thousands of different application protocols. At the bottom, the physical layer, it is also wide open. There are dozens of physical link technologies, fiber, 5G, Wi-Fi, satellite. But in the middle, there is a narrow waist.
And what exactly lives in the narrow waist?
Exactly one single protocol, the Internet Protocol, IP. Everything above it, all the apps, assumes only IP's minimal service. And everything below it, all the physical hardware, only needs to know how to carry an IP datagram.
Why is forcing everything through one single protocol in the middle so crucial? Why not have different network protocols for different types of data?
Because it creates a massive, world-changing, two-sided platform effect. Think of IP as the standardized shipping container of the digital world. Because of the narrow waist of IP, a radio engineer can invent a brand new, revolutionary 6G cellular technology tomorrow. And to deploy it globally, they don't have to ask millions of web developers to rewrite their applications. The 6G tower just needs to know how to carry an IP packet.
And conversely, some kid in a dorm room can invent a brand new video streaming app, and they don't have to ask AT&T or Comcast to upgrade their physical fiber optic cables to support it. The app just spits out IP packets, and the network blindly carries them.
Exactly. It completely decouples software innovation from hardware innovation. If you have n number of applications and m number of physical links, the cost to make them interoperate is n plus m. If we didn't have IP in the middle, every app would have to be custom coded to work with every physical wire. The cost would be n multiplied by m. The internet would have stagnated in the 1980s.
But here's my big pushback. I understand the genius of standardizing on one protocol, but the waist is narrow not just in choice, but in features. IP guarantees absolutely nothing. No reliability, no ordering, no security. Why on earth doesn't the network guarantee delivery? We send highly sensitive corporate data, medical records, and billion-dollar bank transfers over this thing. Why not just make the router smart? Why not make every single router check for errors and automatically retransmit lost packets so the core of the network is flawlessly reliable?
You have just hit upon the most profound architectural debate in the history of networking. The answer to your question is a principle called the end-to-end argument. It was articulated in a famous 1984 paper by Sulzer, Reed, and Clark. Let's play out your idea. Let's say we spend billions of dollars to make every router perfectly reliable. Every single link between every router performs deep error detection and automatic retransmission.
Sounds great to me. I would never lose a packet again. Flawless data transfer.
But is your end-to-end file transfer actually correct?
What do you mean? If the links are perfect, the file is perfect.
Not necessarily. What if the packet arrives perfectly at a router in Chicago, but while it is sitting in the router's memory buffer waiting in line, a stray cosmic ray or slight power fluctuation flips a single bit in the RAM from a 0 to a 1.
Oh.
The router then flawlessly transmits that corrupted packet to the next link. Or what if the hard drive on the receiving server has a software glitch and subtly corrupts the file as it saves it to disk?
The perfectly reliable network links wouldn't catch either of those things.
Exactly. Because data can be corrupted inside the nodes, inside the memory and the endpoints. The receiving application, your web browser, or your bank server still have to perform an end-to-end integrity check. It has to calculate a cryptographic checksum over the entire completed file anyway, just to be safe.
I see where this is going.
Since the endpoints are forced to do the complex reliability check, regardless of what the network does, building massive, complex, expensive reliability features into the core of the network is totally redundant.
So the end-to-end argument says don't force every single packet on the internet, even the ones that don't care about reliability, like a pixel in a live video stream. Don't force them to pay the heavy overhead cost of perfectly reliable router-to-router transfer if the endpoints are just going to double-check the math anyway.
Exactly. Keep the core of the network dumb, incredibly fast, and completely neutral. Push all the complex intelligence, the error checking, and the state, the tracking of the connection, to the endpoints, to the laptops and servers.
And this leads to a sibling principle that has the coolest name in all of computer science: fate sharing.
Fate sharing is beautiful. It dictates that you should store the state of a communication only on the computers that are actually communicating.
Meaning, the routers in the middle of the country don't keep a record that my laptop is currently talking to a server in London. They just mindlessly forward the packets.
Right. And think about the resilience that creates. If a massive core router in the Midwest catches on fire and dies, it loses its memory. If it was storing the state of your connection would be instantly severed.
But because it's not storing my state, my video stream might stutter for a few seconds while the IP control plane reroutes my packets around the smoking crater, but the connection itself doesn't drop. My laptop and the server still hold the state. The connection survives.
Exactly. The only way the connection state is destroyed is if your laptop crashes or the server crashes. But in that case, who cares? If your laptop explodes, you can't watch the video anyway. The connection and the user share the same fate.
It makes the network virtually indestructible. But, and this brings us to a darker chapter in the internet's history, the extreme minimalism of IP had a very heavy cost. Because the IP layer was entirely dumb, it provided no built-in security, no quality of service guarantees for VIP traffic, and no built-in way to bill users for specific services. The massive telecom operators felt they had no control over the beast they built. So the network fought back.
Yes. The operators looked at the dumb core and said, we need to assert control. So they started inserting what we call middleboxes into the network.
What exactly is a middle box?
A middlebox is a device placed directly on the data path that violates the end-to-end argument. Instead of just blindly forwarding IP packets based on the destination address, a middlebox actively intercepts the packet, opens up the envelope, inspects the transport headers, and sometimes even modifies the data on the fly.
Give me a practical example. We are talking about things like firewalls. Right. And NATs.
Yes, firewalls, NATs, which stands for Network Address Translators, Load Balancers, Intrusion Detection Systems. NAT is probably the most famous and the most destructive to the original architecture.
Explain NAT to me, because I know I have a NAT in my home Wi-Fi router, but I don't really know what it's doing.
Back in the 1990s, the internet ran out of pages in its address book. IPv4, the original addressing scheme, only had about 4 billion unique public IP addresses. As the web exploded, we literally ran out. NAT was a desperate, brilliant hack to save the internet.
How does it work?
Instead of giving every laptop, phone, and smart TV in your house a unique global public IP address, your ISP only gives you one public address assigned to your router. Every device inside your house gets a fake, private, internal address that the rest of the world can't see.
Okay, but if I'm on my laptop with a fake address and I request a web page from a server, how does the server know where to send the web page back?
When your packet passes through your home router, the NAT software intercepts it. It rubs out your laptop's private fake address, overwrites it with the router's single public address, and sends it out. But crucially, the NAT router has to create a state table in its memory. It writes down, I changed this specific connection from this internal laptop, and I will remember it. When the server replies to the router looks at the state table, overwrites the address again, and sends it back to your laptop.
Wow. It's intercepting and rewriting the mail on the fly. But wait, you just said it has to maintain a state table in its memory. Doesn't that completely break the rule of fate sharing?
It shatters fate sharing. If your home NAT router reboots or crashes, it loses that entire state table from its memory. Even if your laptop is perfectly fine and the server is perfectly fine, all of your active connections instantly die because the middle box forgot how to translate the addresses.
And firewalls do something even more structurally damaging, don't they?
Much more damaging. Firewalls enforce security policy by looking deep into the headers, and they're generally programmed with a default deny philosophy. If a firewall sees a packet it doesn't recognize or understand, it doesn't forward it, it drops it into the void.
Which leads to a massive problem that you call protocol ossification, the evolutionary ratchet. How did firewalls accidentally freeze the evolution of the internet?
Well, middle boxes are programmed based on the traffic they see today. For decades, almost all internet traffic fell into two buckets at the transport layer. TCP, which is the reliable, strict, certified mail used for web pages, and UDP, which is the fast, reckless, unacknowledged postcard used for voice and video.
Okay, so the firewalls were hard-coded by IT admins all over the world, allow TCP, allow UDP, drop absolutely everything else because it might be a hacker.
Exactly. Then, in the early 2000s, networking researchers realized TCP had some serious performance flaws, so they invented vastly superior transport protocols. A famous one was called SCTP. It was better, faster, and more secure than TCP.
And they tried to launch it to the world.
They tried to deploy it globally, and it failed catastrophically.
Why?
Because as soon as a user's computer sent an SCTP packet, it hit the very first middle box on the path, maybe their home router, maybe their ISP's firewall. The firewall opened the envelope, looked at the protocol number, and said, this isn't TCP, this isn't UDP, I don't know what this is. Drop.
Oh, wow.
The deployed base of millions of rigid middle boxes worldwide had essentially narrowed the narrow waist of the internet from IP to only TCP or UDP over IP. The protocol stack rusted shut. The internet lost its ability to evolve.
It's like an automotive engineer inventing a revolutionary, perfectly street-legal hovercraft that could solve traffic forever. But when they try to drive it on the highway, the automated toll booths are physically hard-coded to only lift the gate for sedans or pickup trucks. The hovercraft shows up, and the gate just stays down permanently.
That is exactly what happened. And it didn't just stop new protocols. It froze the internals of existing ones.
Yep.
Even TLS, the cryptographic protocol that puts the little padlock in your browser and secures the entire e-commerce web, got ossified.
Really? Even the security protocols got frozen?
Yes. In 2018, engineers finished designing TLS version 1.3. It was a massive upgrade, faster, much more secure. But when they tried to deploy it to web browsers, middle boxes all over the world started crashing or dropping the connections simply because they saw a version number in the header 1.3 that they hadn't seen before. The middle boxes panicked.
So how did the engineers ever get TLS 1.3 deployed? We use it today, right?
They had to lie. They had to disguise it. The engineers intentionally designed TLS 1.3 to masquerade on the wire as an old TLS 1.2 session resumption. They had to fake the unencrypted headers, keeping old obsolete fields intact, just to sneak the new secure payload past the brittle middle boxes without triggering a panic.
That is absurd. The engineers building the internet had to resort to camouflage just to upgrade it, which leads perfectly to the endpoint countermove. If the network is actively hostile to innovation, what do the app developers do? They initiate cryptographic opacity.
It is a technological Cold War. Modern protocol designers realized a fundamental truth. If a middle box can parse a field in clear text, it will eventually write a rigid rule about it and ossify it. So the new rule of internet design is encrypt absolutely everything observable.
Blindfold the network.
Exactly. Take QUIC, for example. QUIC is the revolutionary transport protocol developed by Google that now powers a massive chunk of the web. It runs inside UDP because firewalls still blindly let UDP through. But virtually every single piece of metadata inside the QUIC packet, the sequence numbers, the control flags, the transport headers, is cryptographically scrambled.
So when a corporate firewall or an ISP intercepts a QUIC packet, it just sees a stream of meaningless random noise. It can't read the sequence numbers, so it can't try to optimize the flow. It can't see
Mhm.
the options, so it can't make rigid rules dropping unknown versions. The middle box is forced to just shrug and forward the packet, returning the internet to the dumb, fast core it was meant to be.
And the engineers didn't stop there. They introduced a brilliant maintenance discipline called grease.
Grease. Like oiling a machine. What does it stand for?
Generate random extensions, and sustain extensibility. Since the very first day of deploying these new encrypted protocols, the engineers deliberately inject completely meaningless random garbage values into the few unencrypted extension points in the headers.
Wait, they are purposely wasting bandwidth sending garbage data. Why?
To train the middle boxes, if an extension field is left empty for 5 years, some middle box developer will eventually write a lazy line of code that says this field must always be 0, drop the packet if it's not. By constantly injecting random grease values into those fields every single day, if a developer writes a rigid rule, their middle box will break and fail loudly on day 1 during testing.
It forces the middle boxes to stay flexible by constantly exercising the joints of the protocol. It's like doing mandatory network yoga to keep the firewalls from stiffening up.
Eh.
Okay, so we have this wildly complex, opaque, encrypted, heavily ossified network where packets are bouncing through invisible queues. How does anyone actually see what's happening? If the network is this blind, how does anything get fixed when it breaks? Let's dive into our final section, measuring the invisible network. Walk me through the diagnostic toolkit.
Network engineering is a deeply empirical discipline. The mathematical theory is nice, but measurement is reality. The very first tool every engineer learns is ping.
Ping.
Yeah.
Absolute classic. How does it actually work?
It uses a specialized control protocol called ICMP to send a tiny echo request packet to a destination IP address. The destination server receives it and is obligated to immediately send an echo reply back.
So it measures the round trip time, the RTT. And based on what we discussed earlier about delay, if I ping a server 100 times in a row, the absolute fastest ping in that batch, the minimum RTT, that is my hard physical floor, right? That is purely my propagation delay plus my transmission delay with 0 waiting in line.
Yes. The minimum is the deterministic floor dictated by the speed of light and your link speed. But the real insight comes from looking at the variation above that minimum. If your fastest ping is 20 milliseconds, but your average ping is 150 milliseconds, that massive spread reveals the instantaneous queuing delay. You are watching the buffers fill and drain in real time. That variance is called jitter, and it is what completely ruins real-time voice and gaming.
But I've heard you have to be careful trusting ping entirely.
You do, because routers are heavily optimized to forward normal data packets in hardware. ICMP ping packets are considered management traffic, so they're often punted up to the router's slow software CPU to be processed. If a router is busy, it will intentionally delay or drop your ping to protect its CPU. So ping might tell you the network is congested and dropping packets, when in reality your actual Netflix video packets are flowing through the hardware data plane perfectly fine.
Easy to know. Tool number 2 is traceroute. I have always loved traceroute because it feels like an elegant abuse of a fail-safe mechanism.
That is exactly what it is. Every IP packet has a field in its header called time to live, or TTL. It's essentially a hop counter designed to prevent packets from looping endlessly in a circle if the routing tables have a bug. Every time a router processes a packet, it decrements the TTL by 1.
And if the TTL hits 0,
The router is mandated to drop the packet, kill it, and send an ICMP time-exceeded error message back to the original sender.
So traceroute weaponizes this rule. It intentionally sends a packet toward the destination with a TTL of exactly 1. The very first router it hits, your home router, decrements it to 0, drops it, and sends an error message back. And boom, now your computer knows the IP address of hop number 1.
Then it sends a packet with a TTL of 2. The first router drops it to 1 and forwards it. The second router drops it to 0, kills it, and replies. Now you know hop 2.
It's like mapping a pitch-black cave by throwing rocks deeper and deeper and listening for where they hit the wall. It maps the path across the globe.
It is brilliant. But again, it is arguably the most misread tool in networking. A lot of junior IT people will run a trace route, see a massive latency spike at, say, hop 4 in the middle of a backbone, and confidently declare, router 4 is congested. That's the problem.
Why is that wrong?
Because the time reported by traceroute is the round trip time. It includes the time it took the error message to travel on the return path back to you. And importantly, on the modern commercial internet, routing is highly asymmetric. The path your packet takes to Google is almost never the same physical path Google's response takes back to you. So a delay in hop 4 might actually be delay on the invisible return path that you can't even map.
And what if a hop just shows up as asterisks? Does that mean the cable is cut?
Rarely. A missing hop usually just means a core router is configured by its admin to silently ignore 0 TTL packets because generating those error messages wastes CPU cycles. It is hiding its identity, but it is still forwarding your real traffic perfectly fine.
Okay, tool 3 is IPER3.
While ping measures delay, IPER3 measures true throughput. It blasts a continuous stream of random data memory to memory between two hosts that you control. It completely bypasses your slow hard drive and tells you exactly what the TCP congestion control algorithm is physically capable of achieving on that specific path.
And finally, tool 4, the ultimate weapon, TCP dump or Wireshark.
This is the ground truth. This is packet capture. It records the literal frames, the raw ones and zeros, exactly as they arrive at your network interface card. You can open that file in a graphical tool like Wireshark and visually peel back the encapsulation layers. You can see the Ethernet frame, the IP header, the TCP flags. You can physically verify the encrypted opacity of QUIC. You can calculate the exact millisecond timestamps of a queuing delay. It doesn't lie.
Let's tie all of this theory, the delays and the tools, together with a real-world scenario, the diagnostic loop. Let's say a user sitting in a coffee shop in Guatemala City is trying to fetch a simple 2-megabyte PDF file from a corporate server located in Frankfurt, Germany. They call the help desk and complain that the app feels incredibly sluggish and slow.
Okay, let's play detective and do the physical arithmetic of the delay. First, propagation delay, the speed of light, from Guatemala City to Frankfurt is roughly 9,500 kilometers of submarine fiber optic cable.
Light and fiber takes about 5 microseconds per kilometer. So 9,500 times 5 is 47,500 microseconds, which is 47.5 milliseconds. Add a few milliseconds for the messy local access segments to get to the submarine cable landing station, and we are at a one-way physical delay of about 52.5 milliseconds.
Correct, which means the absolute minimum round-trip time, the RTT, is roughly 105 milliseconds. Now remember that modern protocols like TVP and TLS require a full round-trip handshake, sending a hello and waiting for an acknowledge, just to set up the connection and negotiate encryption keys before any actual file data can flow.
So the user clicks the link and 105 milliseconds vanish instantly just saying hello.
Yes. Now, what is the bottleneck bandwidth? The user is on coffee shop Wi-Fi. Let's say it's decent, providing a realistic 100 megabits per second throughput.
Now we calculate the transmission delay. A 2-megabyte file is 16 megabits of data. 16 megabits divided by the 100 megabits per second pipe gives us 0.16 seconds, which is 160 milliseconds of pure transmission time to push the PDF onto the local airwaves.
Finally, we add queuing delay. The coffee shop router is slightly congested with other people browsing, so it adds, let's say, a modest 5 milliseconds of wait time in the buffer. Total it all up.
105 milliseconds for the speed of light setup, plus 52.5 milliseconds one-way propagation for the first chunk of data to arrive, plus 160 milliseconds of transmission time, plus 5 milliseconds waiting in line. The user experiences a total delay of about 322 milliseconds.
Over a third of a second. It feels sluggish.
Yeah.
But look at the arithmetic of where the time actually went. Half of it is completely dictated by the speed of light and protocol handshakes across the ocean, and the other half is the Wi-Fi transmission.
This is where it gets revelatory. If that user gets frustrated and tells the coffee shop owner to pay their ISP to double their internet speed to 200 megabits per second,
They will barely notice a difference. They only have the transmission time. They save maybe 80 milliseconds. The speed of light across the Atlantic hasn't changed. The handshakes still take 105 milliseconds.
but if the corporate IT department takes that PDF and places it in a CDN cache, a server physically located directly in Guatemala City.
Now, the physical distance is a few miles instead of 9,500 kilometers. The propagation delay drops to almost zero. The 105 millisecond setup time vanishes. The user gets a massive instant performance boost without changing the coffee shop's internet speed at all. This arithmetic is so decisive, it proves that you cannot fix a distance problem with bandwidth.
It is the absolute first tool you have to reach for in any performance investigation. You have to understand the physical reality underlying the digital experience.
You do. You have to hold both realities, the messy physics and the logical service, in your head at once.
This has been an incredible journey. We started with a chaotic web of physical wires, this infrastructure view that looks like a tangled mess of competing companies. We explored how the mathematical gamble of statistical multiplexing, relying on the bursty nature of human behavior, actually makes it cheap enough to exist.
We saw how the end-to-end argument and the hourglass model push all the intelligence to the edges, creating a dumb neutral core that sparked a trillion-dollar explosion of software innovation.
And we saw the unintended consequences. The telecom network operators, starved of visibility and control, deployed middle boxes and NATs that accidentally froze the protocol stack. And the brilliant engineers at the edges responded by encrypting the entire transport layer to keep the internet evolving.
Which leaves us with a truly provocative final thought to ponder. If we project this current trajectory forward, the endpoints, the apps on your phone, are now heavily encrypting almost all their traffic to bypass middle boxes. QUIC, TLS 1.3, it is completely opaque.
Right.
This means the massive network operators, the AT&Ts, the Comcasts, the Vodafones of the world, are rapidly going completely blind. They are losing all visibility into the specific flows of data on the physical cables they own. They can't see if a packet is a video stream, a file download, or a voice call.
Which means they can't monitor it, they can't optimize their queues for it, and crucially, they can't monetize specific types of flows by charging premium tolls.
Exactly. So if the companies laying the billion-dollar submarine cables and erecting the 5G towers can no longer read or control the traffic flowing over their assets, will they eventually retaliate?
How could they retaliate if they can't read the packets?
By defaulting to hostility. Will we see a future where operators simply start aggressively throttling all unrecognized, heavily encrypted traffic out of spite or self-preservation? If they can't identify it, they slow it down to 1 megabit per second.
Wow. We might be shifting from a universally open, permissionless internet into an era where the web fractures into heavily gated zero-trust fiefdoms. An internet where if your highly encrypted application traffic isn't officially recognized or hasn't paid a premium toll to the physical operator, it just gets dropped to a crawl.
It is a profound geopolitical and economic tension happening right now, silently, at the packet level.
Yeah.
It is a war for control of the hourglass.
Keep that in mind the next time you browse the web and get frustrated by a buffering video. The internet isn't a master-planned, tranquil city. It is a chaotic, wildly complex ecosystem of competing physical forces held together by sheer probability, cryptographic armor, and a 50-year-old promise to just give it a best effort.